Welcome to The Explainer. Today, we are diving into a really powerful idea, one that could completely change how you think about collaboration and even arguments.
So let's get right into it. The whole story kicks off with a simple meeting that kind of went off the rails. And this one quote, there was dissonance. It just perfectly captures that moment, that feeling when a whole room of smart people realize they're looking at the exact same thing, but seeing totally different worlds.
Okay, so picture this. You've got a room with three groups of people. They're all experts, right? You've got your university mathematicians, you've got physicists, and you've got high school math teachers. And they're all there for one reason, to try and make math education better.
So they're handed this calculus problem, something straight out of a high school exam. The task? Find the asymptotes for this function. Now you'd think for a room full of experts this would be a piece of cake, but it really wasn't.
The physicists, they take one look at it and basically say, oh, that's easy. As x gets huge, that natural log part becomes pretty much irrelevant. The function just behaves like the line y equals x. Simple, right? But that quick, confident answer, it absolutely floored the teachers.
See, the teachers, they knew this problem inside and out from their own curriculum, and they were sure that was the wrong answer. For them, for their students, the function does not behave like the line y equals x. So, who's right? I mean, how can all these brilliant people look at the same equation and come to completely opposite conclusions? And this is where it gets really fascinating. The root of the problem wasn't the math, it was the unspoken definitions they were all using. For the teachers, asymptotic behavior was all about the difference. You know, does the physical gap between the curve and the line actually shrink to zero on a graph? And for this problem, the answer is no. But the physicists, they were thinking in terms of ratio. Does the ratio of the function to the line get closer and closer to 1? And for that, the answer is yes.
So that leads to a really interesting question, right? Which definition is actually better for high school kids? The teachers made a great point. Their difference definition is way more visual, more concrete for graphing. Does the curve physically get closer? But the physicists, they valued the ratio view for seeing the big picture, the larger patterns. The thing is, there's no single right answer here. The one you pick says a lot about what you think is important.
Now, this whole puzzle isn't just some quirky math problem. Nope. It actually shines a light on a huge challenge we all face when we try to work together, especially when we're coming from totally different worlds. The source uses this fantastic word to describe the situation, incommensurable. It basically means their perspectives were so different, they were operating on completely different playing fields. An argument from one side, like, hey, this is better for teaching, was just irrelevant to the other side's goal of, well, this is more useful in actual science. They were completely talking past each other.
And that brings us to a really big idea about teamwork itself. You know that classic image of collaboration, where a diverse group talks and talks and talks until everybody finally agrees on one thing? Well, the source basically says that's a myth. For groups with real deep differences, that model just doesn't work.
So, that leaves us with a pretty big question, doesn't it? If getting everyone to agree is basically a fantasy, then how on earth can groups with such different ways of seeing the world actually get anything done together? Well, this is where a much cooler, much more powerful idea comes in.
The answer is something called a boundary object, and it's a game changer. It's a tool that's specifically designed to help people cooperate without having to agree on everything.
So what is it? A boundary object is basically something concrete. It could be a map, a document, a prototype. Heck, it could even be a math problem. It's something that people from different groups can all gather around and work with, even if they're seeing it and using it in totally different ways.
For one of these things to actually work, it needs two key ingredients. First, it's got to have a common structure, something everyone can look at and say, okay, I know what that is. And second, it needs what's called interpretive flexibility. That's a fancy way of saying it has to be loose enough for different people to bring their own ideas and methods to it. And that brings us right back to our calculus problem. It was a perfect boundary object. It wasn't just the thing that started the fight, it was also the very tool that helped them figure it out.
So, think about it. It had that common structure, right? Everyone in the room recognized it as a standard calculus problem. But it also had that flexibility. The physicists saw it as a zooming out tool for big picture physics. The teachers saw it as a graphing tool for students. And because it had both, it did something incredible. It made their hidden disagreement visible. Suddenly, the conversation wasn't about who was right or wrong. It was about why they saw the same things so differently. That's a huge shift.
And this isn't just some fluke, some one-off story. Once you get this concept of a boundary object in your head, I'm telling you, you start seeing them everywhere. The source points out a bunch of them just from the world of education. Things like a homework assignment, a specific math concept, or even a video recording of a classroom. All of these can act as boundary objects. They can help bridge the gap between, say, students and teachers, or between researchers and the people actually in the classroom.
And here's another great real-world example. Back in the 90s, a group of education researchers did something smart. They invited mathematicians to come watch videos of fourth-grade math classes. Those videos, they became the boundary object. They were this concrete, shared thing that allowed two very different groups to have a real, productive conversation. And out of that, they built a whole new, influential field of study together. How cool is that?
Okay, so what's the big takeaway here? Why should you care about a kind of academic-sounding concept like this? What does it mean for your work or just your life?
Here's the most important part. A boundary object completely reframes what a disagreement is for. The goal isn't winning the argument anymore. It shifts to understanding the different perspectives. It turns what could be a battle into a shared journey of discovery.
And the key is, you don't all have to agree in the end. The goal is to find what the source calls complementary purposes. It's about finding ways your different goals can actually work together, or at least exist side by side, so the whole group can move forward together. No one has to give up their unique point of view. And that brings us to one last question for you to think about. In your own work, on your own teams, wherever you collaborate with people, where is there a disagreement that just won't go away? And what is the shared thing, the map, the prototype, the document, the boundary object that you could put in the middle of the table to turn that frustrating argument into a genuine discovery?